Hello everyone, I'm Hariharan and today I'll be presenting on a fascinating and futuristic topic, quantum key distribution where physics meets cryptography. This topic is a part of network security and cryptography. And over the next 20 minutes, I'll walk you through how quantum mechanics, the science of very small, is transforming cybersecurity. We'll understand why our classical encryption systems are at risk from quantum computers, how quantum key distributions or QKD works, what makes it unbreakable, and how it's already being implemented around the world, including here in India. Let's begin our journey into the world where physics ensures security. Introduction to quantum cryptography. Before we dive into QKD, let's see the stages with some basics. Classical cryptography, which we use today in systems like RSA, AES, and PCC, is based on mathematical hardness. For example, RSA security depends on the difficulty of factoring large prime numbers. But quantum cryptography is different. Instead of relying on math problems that are merely hard to solve, it uses the fundamental laws of physics to ensure security. This is the revolutionary part. It's unconditionally secure, meaning even if infinite computing powers, it cannot be broken because nature itself enforces the protection. So, unlike classical cryptography, where security is based on assumptions, quantum cryptography provides security guaranteed by physics itself. Why classical cryptography is at risk? Now, why do we even need quantum cryptography? The reason is simple. Quantum computers, algorithms like short algorithms can efficiently break RSA and elliptic curve cryptography. To give you a perspective, a strong RSA key today might take a classical supercomputer millions of years to break. But with the powerful quantum computers, it could be done in seconds. This means that our existing internet security, banking, passwords, national defense could all become vulnerable once large scale quantum computers are available. So, this is not just theoretical, it's an urgent, real world concern. That's why scientists are racing to build quantum safe security systems like QKD. What is quantum key distribution? Quantum key distribution or QKD is a method that allows two parties, we usually call them Alice and Bob, to generate and share secret encryption keys securely, even over a potentially insecure communication channel. Here's the interesting part. Instead of relying on mathematics, QKD uses photons, the particles of light, to encode informations. The protocol works because of a unique property. If anyone, say an enveloper named Eve, tries to intercept or measure these photons, their quantum state gets disturbed. This immediately alerts Alice or Bob that the communication is being tampered with. So, security here is not just theoretical, it's physically guaranteed by the laws of quantum mechanics. That's what makes QKD revolutionary. Core quantum principles behind QKD. Let's understand the three quantum principles that make QKD possible. First, Heisenberg's uncertainty principle. Secondly, quantum superposition. Third, no cloning theorem. Let's see each of them one by one. First, Heisenberg's uncertainty principle. When you observe a quantum particle, you change its state. So, if Eve tries to read the photons, Alice and Bob can detect the disturbance. Second, quantum superpositions. A photon can exist in multiple states at once until someone measures it. Once measured, it collapses into one definite state. This ensures that any unauthorized observation leaves traces. Third, no cloning theorem. It's a physically impossible to make a perfect copy of an unknown quantum state. That means Eve cannot duplicate photons without being detected. These three principles together make QKD thoroughly secure. No amount of computing power, Not even a future quantum computer can bypass the law of physics. The BB84 protocol overview. The first and most famous QKD scheme is called BB84, developed in 1984 by Charles Bennett and Gilles Bizarre. In BB84, bits, zeros and ones are encoded in the polarization of photons. There are two bases, rectilinear, positive. Horizontal represents 0, vertical represents 1. Diagonal, multiplication. 45-degree represents 0 and 135-degree represents 1. Even though BB84 was introduced in 1984, it's still the backbone of most QKD's system today. For example, ID Quantic, a Swiss company, has implemented BB84 based system for governments and banks across Europe and Asia. In fact, the Swiss federal election in Guinea used a QKD system to secure data transmission between polling centers. That's a real world democratic application of BB84. Now, let's see the working step of this protocol. Alice sends photons with random polarization and Bob measures them using randomly chosen bases. Later, they compute which bases they used, keep only the matching ones, and discard the rest. This becomes their shared raw key. If any eavesdropping is detected during verification, the process is repeated until a clean key is generated. So, this is what break down into four steps and carry forward. First step, photon transmission. Second, random measurement. Third, basic reconciliation. Fourth, key shifting. Eavesdropping detection. Here's the beauty of QKD. It can detect eavesdropping automatically. When Eve tries to measure the photons, changes their state. This introduces errors. When Alice and Bob compass a small sample of their bits, they can calculate the error rate. If it's higher than the expected noise levels, they know someone is listening. In that case, they simply discard the key and restart the protocol. In short, in quantum communication, you can't spy without being caught. For example, in China's Messias satellite experiment, scientists intentionally tried to stimulate eavesdropping. They found that even the smallest inference by external instrument increased the error rate instantly, confirming that the system could detect instructions in real time. That's like your Wi-Fi router automatically detecting if someone even tries to peek at your data. But this is at quantum level. Key distillation process. Once Alice and Bob confirm that no eavesdropping has occurred, they go through three refinement stages to get a perfect final key. First, error correction. Second, privacy amplification. Third, authentication. Let's see each one by one. First, error correction. They use classical codes to fix small differences caused by noise. Second, privacy amplification. They apply hash functions to remove any leaked informations, ensuring even partial data cannot help Eve. Third, authentication. They verify each other's identities to prevent impersonation or man in the middle attack. After this process, the final key is absolutely secure. It's ready for use in encryption systems like one time patch or hybrid quantum classical protocols. QKD versus classical key exchange. Let's compare classical and quantum key exchange. In classical cryptography, security is based on mathematical hardness, which can be broken by quantum computers. In QKD, security is based on physical laws, so it's unconditionally secure. Classical methods can't detect eavesdropping while QKD always can. And importantly, quantum keys are future proof. Even if data is recorded today and decrypted years later with quantum machines, it won't work if QKD was used. For example, let's take cloud computing as comparison. Traditional cloud storages like Google Drive or AWS relies on classical encryption. But if someone steals your key or decrypts it later using a quantum computer, your data is exposed. Meanwhile, Quantum cloud systems like the ones IBM and AWS are researching can use QKD to exchange keys safely, ensuring that even future quantum attack can't recover old data. Real world applications of QKD. Now let's see where QKD is actually being used. Banking and finance. Banks like China's ICBC and UBS in Switzerland uses QKD to secure interbank transaction worth billions. Defense and government. QKD secures military communications and satellite links. Healthcare. Hospitals can protect sensitive medical records with quantum secure channels. Cloud infrastructure. Companies like IBM and Toshiba are developing quantum safe cloud systems. Quantum Internet. This is the ultimate goal, an internet built entirely on quantum communications for unhackable connectivity. So, QKD isn't science fiction, it's being deployed right now. Global QKD implementations. Let's look at how different countries are adopting QKD. China, the Mississippi satellite demonstrated quantum communications over 1200 kilometers, the world's first space-based QKD. Europe. The Europe QCI initiative is connecting EU countries with quantum networks for critical infrastructure. India. In 2021, ISRO and DRDO conducted successful quantum communication trials over 300 meters, marking India's entry into the quantum race. USA and Japan. They are developing commercial test based that integrates QKD with existing telecom systems. These efforts show that QKD is becoming a global priority, especially for data sovereignty and national security. Challenges and limitations. Of course, QKD isn't perfect yet. There are still challenges. High cost of specialized equipment like photon source and detectors. Distance limits. Fiber-based QKD can only go up to about 200 km before signals degrade. Environmental sensitivity. Quantum states are easily disturbed by noise, heat, and vibration. Quantum repeaters are still in development, and integration with existing network is complex. However, these challenges are actively being solved by research groups and startups around the world, including in India under the National Quantum Missions. The future of QKD. The next decade will be a breakthrough era for QKD. Integration with 5G and 6G networks will make mobile communication quantum safe. Global satellite QKD systems will allow secure communication across continents. Hybrid models will combine post quantum cryptography with QKD for layered defense. And eventually, we'll have a quantum internet enabling distributed quantum computing and fully secure global networks. For example, now let's talk about where this is heading. 5G and 6G integrations. Companies like SK Telecom in South Korea are embedding QKD into their 5G infrastructure for ultra secure communications. Global satellites. China plans a constellation of 20 quantum satellites by 2030. Hybrid systems. IBM and Google are combining post quantum cryptography with QKD for layered protection. Quantum Internet. DARPA in the US and C. in India are both working on building the foundation of a quantum internet where every communication node is quantum secure. To conclude, the shift towards quantum secure communication is not optional, it's inevitable. Take India's C. Quantum Communication Lab. It's already developing indigenous QKD system for defense and government networks. And as cyber threats evolve, this physics-based approach will redefine how we protect sensitive information. So, whether it's a hospital in Singapore, a satellite in China, or government office in Delhi, quantum key distribution is shaping the future of global security. To wrap up, quantum key distribution represents a major shift in how we think about security. It doesn't depend on algorithm or computational limits. It's security guaranteed by physics. It can automatically detect eavesdropping and ensure that even quantum computers can't break it. As we move into the post quantum world, technologies like QKD will become essential for banking, defense, healthcare, and global communications. In short, the future of cybersecurity lies not in stronger math but in smarter physics. In conclusion, quantum key distribution is not just a research topic, it's the foundation of the next generation of secure communication. Thank you for listening, and I hope this lecture helped you see how quantum technology is transformed cybersecurity from mathematical protections to physical assurance. Thank you.